Things that move back and forth, to and fro, or up and down are vibrating. A vibration is a periodic wiggle in time. A periodic wiggle in both space and time is a wave. A wave extends from one place to another. Light and sound are both vibrations that propagate throughout space as waves, each being very different kinds of waves. The sound that little Abby produces with her cello is a mechanical wave, sound, the propagation of vibrations through a material medium, the air. Or it can propagate through a solid or liquid. If there's no medium to vibrate, then no sound is possible. Nephew John boosts his sound electronically. However produced, sound cannot travel in a vacuum. But light can, which is evident when it propagates through the vacuum between the sun and Earth. We'll learn in later lessons that light is a vibration of electric and magnetic fields, an electromagnetic wave of pure energy. Although light can pass through many materials, it needs none. The source of all waves, mechanical or electromagnetic, is something that is vibrating. Let's define some terms that relate to vibrations and waves. The shape of this wave approximates a sine curve. We call the high points crests and the low points troughs, as in a water wave. Amplitude refers to the distance from the midpoint to the crest, or trough, of the wave. The wavelength is the distance from the top of one crest to the top of the next crest, or equivalently, the distance between any successive identical parts of the wave. We express wavelength with the Greek letter for length, lambda. The wavelengths of waves at the beach are measured in meters, the wavelengths of ripples in a pond are measured in centimeters, and the wavelengths of light are measured in billionths of a meter, nanometers. How frequently a vibration occurs is described by its frequency. Frequency specifies the number of to and fro vibrations occurring in a given time, usually 1 second. A complete to and fro oscillation is one vibration. If it occurs in 1 second, the frequency is 1 vibration per second, or 1 hertz. The unit of frequency is called the hertz, after Heinrich Hertz, who demonstrated radio waves in 1886. 1 vibration per second is 1 hertz. 2 vibrations per second is 2 hertz, and so on. Higher frequencies are measured in kilohertz, that's thousands of hertz, and still higher frequencies in megahertz, millions of hertz, or gigahertz, billionths of hertz. A radio station that broadcasts at 101.7 megahertz on the FM dial transmits radio waves having a frequency of, that's 101,700,000 hertz. The same frequency at which electrons are forced to vibrate in the antenna of the radio station's transmitting tower. Electrons are made to slosh up and down at 101.7 million times each second. How about that? We emphasize again that the source of all waves is something that vibrates. Normally, the frequency of the vibrating source and the frequency of the wave it produces are one and the same. The period of a wave is the time for one complete vibration. If an object's frequency is known, its period is the reciprocal. If the frequency of vibration is 2 hertz, the time needed to complete one vibration, the period of vibration is 1/2 second. Or if the vibration frequency is 3 hertz, then the period is 1/3 second. Both period and frequency are reciprocals of each other. The speed of a periodic wave, like any speed, is defined as the distance divided by time. Let the distance be 1 wavelength. Then the time is 1 period. So, wave speed equals wavelength over period, and knowing 1 over period is frequency, we see that the equation for wave speed becomes wavelength times frequency. It's common to say wave speed equals frequency times wavelength. This relationship holds true for all kinds of waves, whether waves on a stretched string, sound waves, or light waves. Here's a simple problem that illustrates wave behavior. What's the speed of a water wave that oscillates up and down 3 times each second when the distance between wave crests is 1 meter? Here the frequency of the wave is 3 Hz. Its wavelength is 1 meter. The speed v of the wave at the water surface, as with waves in general, is expressed as v equals f lambda. Notice that the unit Hertz is the unit 1/seconds. So we see that wave speed equals 3 meters per second. Got the idea? Let me leave you with a question. Given that the speed of sound in air is 340 meters per second, and sound frequency is 34 Hertz, what is the wavelength of this sound? Until next time, good energy.